Good morning, physics. All right, in this video, I'm going to be talking about the work energy theorem. Now, the work energy theorem is basically the idea that any time energy has been lost, it has been lost due to work done by non-conservative forces. That is usually going to be thermal energy. So, for example, if I kicked a chair and sent it sliding across the floor, it has kinetic energy, right? Because it's moving. It has to have kinetic energy. I did work to get it moving, and that I turned that work into energy. It now has that energy. Well, is that chair going to keep moving forever? No, it's going to stop. When it stops, all of the kinetic energy that I imparted to it has been lost because of the friction between the chair and the floor. And so the distance that it traveled times the frictional force would be equal to the work done, and that work would have to be equal to the kinetic energy that it had when it started. So you can actually use energy to solve some kinematic problems with the work energy theorem. But I'm getting a little ahead of myself. So let's first look at the root equation for the work energy theorem. And that is simply that work is equal to the change in mechanical energy. Now remember, mechanical energy is equal to KET plus KER plus PEG plus PEE, or the sum of translational and rotational kinetic energy and gravitational and elastic potential energy. And change in means final minus initial. So this equation is real nice and pretty at first, but once we plug everything in, and I'm not even actually going to plug in these equations, this becomes that according to the work energy theorem, work can be set equal to KET plus KER plus PEG plus PEE final minus KET plus KER plus PEG plus PEE initial. So this is the work energy theorem without these little equations actually plugged in. Now, the way I personally recommend you do this, you do not have to memorize this equation. If you memorize, my head's in the way. If you memorize these three little pieces, which you need to know this anyway, but if you memorize these pieces, then you can put this together. But an easier way to do it is to say, okay, initially, what kind of energy do I have? So, for example, let's go with the kicked chair. Okay, I kicked the chair, and once I kicked it, it had kinetic energy. And so for our work energy theorem, we would say that the work is equal to the final minus the initial. Well, all it had initially was translational kinetic energy. So that would be our only initial value. What did it have at the end? What kind of energy did it have after it stopped? None. It didn't have any. It didn't have any mechanical energy anyway. All of its energy was expended. I put energy into it when I kicked it, and it slid across the room until friction had taken all of that energy away. So the final energy is 0. So then we find that the work done is equal to the kinetic energy that was lost. And so using that, we can move to the top of the board because I don't plan well. We'll take this and come back up here. We know that work is equal to force times distance, or the distance traveled. So then the force that did the work was friction, because that's what was taking the energy out, times the distance that it traveled would be equal to the mass of the chair times the initial velocity of the chair squared over 2. Now, we're not actually going to do anything with this, but this is how you would get to the actual useful equation part. You have to start with something like this, but you don't necessarily have to actually write all these out so much as you need to go through and say, well, when it was done, did it have translate? No. No. It wasn't above the ground. It wasn't stretching or compressing. So that's how you would turn one of these into a problem. Now, I'm going to do a problem out of the book, so give me just a second. All right, we are going to do problem 47 from page 156, and that's up here if you missed that. I'm going to read it out. A skier starts from rest at the top of the hill that is inclined 10.5 degrees with respect to the horizontal. So theta is 10.5. The hillside is 200 meters long. So the slope, the hypotenuse, is going to be 200 meters. And the coefficient of friction between the snow and the skis is 0.0750. At the bottom of the hill, the snow is level and the coefficient of friction is unchanged. So here's our hill, then the snow becomes level, coefficient of friction stays the same, so he continues on. How far does the skier glide along the horizontal portion of the snow before coming to rest? So, this problem is a little bit of everything. Now, we do not need to do a free body diagram for this. And some of you are going, what? We can do this with energy. Now, to do the first part, we have to do some conservation of energy, but this should be stuff that you guys are familiar with, and I will make a separate video going through some of the background on that. In fact, I think that's the next one, is conservation. Conservation of energy says that the energy at the top of the hill has to be equal to the energy at the bottom of the hill. So at the top of the hill, we have gravitational potential energy. And I am going to change colors for this. So up here we have PEG. As you ski down the hill, your gravitational potential energy gets transferred into translational kinetic energy. And at the bottom of the hill, 100% of your gravitational energy has now become translational kinetic energy. So we can say then, using the law of conservation of energy, which I know we haven't talked about yet, but we'll get there. We can say that these two have to be equal. So PEG has to be equal to KET. So then, if we can calculate the energy here, we can calculate how much energy we have here. And then we're moving until the skier comes to rest. So over here at rest, V is going to be 0. At this point, energy is going to be 0 because work will have been done to take away all of the energy that the skier had. So we can use the work energy theorem for this portion of this problem. So here, the only energy we have at the beginning of this, much like the chair example, is kinetic energy. So the kinetic energy, KET, has to be equal to the work. And so that is going to be equal to the force of friction, which is acting on the skis to slow them down, times S, the distance traveled, which is what we are looking for. So we actually don't need KET. So PEG is going to be mgh equal to Fs. And the force of friction, should have done this first. The force of friction will be equal to our normal force times the coefficient of friction. So then this equation will be Fn mu s. And I'm going to write this up here to clean that up a little bit. So Fn times mu times s, where s is what we're looking for. This is a horizontal problem, so we know from our chapter 4 that Fn has to be equal to the weight of the skier. So Fn would be equal to Fg, which would be equal to the mass of the skier times the gravitational acceleration, which means that all we really need, because m, the mass of the skier, and g, the acceleration of gravity, will cancel out. So height is equal to the coefficient of friction times the distance traveled is all that we really need. So we just need to find the vertical component of this triangle. That's opposite. So then the height will be equal to 200 times the sine, because it's opposite, of 10.5. And then we also have the coefficient of friction. So I'll get this number, and I'll pause it while I do that. And that comes out to 36.4 meters. That's the initial height. So then we take this number and we plug it back in here. So I'll rewrite that equation. Again, H is equal to the coefficient of friction times the horizontal distance traveled after we reach the bottom of the hill. So H we know, mu we know, we need to solve for S, so we divide by mu. H over mu will give us S, so that's going to be 36.4 divided by our 0.0750. And that comes out to 485.33 repeating, or 485 meters. Now, here is one problem with the work energy theorem, which you may have noticed. A lot of times, the work energy theorem works hand in hand with the law of conservation of energy. This is why I am going to make certain that you see conservation of energy before you take the work energy theorem quiz, which we've got like a week before that quiz. On the work energy theorem quiz, there will not be any conservation of energy. You will not have to use conservation of energy on that quiz. You will have to use conservation of energy in tandem with work energy theorem a couple of times in the homework, and it will be at least one on the test like that as well. So, something to keep in mind. But it's going to be something fairly simple like this part up here was. This problem looks super complicated when you first look at it, but energy simplifies things way down. So we don't have to do as much math as was required with kinematics. We had pages and pages of equations when we did kinematics and forces. Energy simplifies those calculations down for us. So that's one of the advantages there. We didn't have to calculate the horizontal component of his speed and the vertical component of his speed and see how fast he accelerated in both dimensions so that we could figure out how fast he was going at the bottom of the hill, and then account for friction to figure out the acceleration to find how far he traveled when his v final was 0. We didn't have to do any of that, which we would have had to if we were doing kinematics. If we did this using chapters 3 and 4 information. So energy will simplify your calculations down quite a bit. Most people really like energy, and this is one reason why. So that is work energy theorem. Again, if you have any questions, let me know. There was something I wanted to mention. So I'm going to pause this recording, see if I can remember what it is, and then come back and tell you. Or come back and tell you that I couldn't remember. One or the other. Okay, it's been a couple minutes and I can't remember. I can't think of what it might have been. So I'm going to assume that we're good, and if I remember it later, I will put it in the description of this video or tell you in class. Probably both, to be honest. So that's it for this video. If you want me to go through maybe a simpler work energy theorem problem, let me know. But that is it for this. I hope you guys learned something. Have a wonderful night, and I'll see y'all back in class.